Welcome to Visual Calculus, an introduction and an overview to prepare students for a full year AP or college level calculus class. Now, to start at the very beginning, calculus is about change. But that doesn't really tell us very much if we're new to the topic. So let's try one level deeper. Calculus is about asking and answering two kinds of questions. One, what is the rate of change of a function? And that's represented by these blue tangent lines. And two, how does that change accumulate? And that's represented here by these blue rectangles, about which we'll have quite a bit more to say shortly. These represent the two principal branches of calculus, differential calculus and integral calculus. Even that, though, probably doesn't do anything for a first-time visitor to the topic of calculus. So I've tried something else that might give you a better handle on what it is that you're about to study. Let's talk about what can be done with and without calculus. So for example, if I want to build a simple house and make sure that the walls are strong enough to hold up the roof, I don't need calculus. On the other hand, if I want to build something like this is the Disney Concert Hall in Los Angeles, I'm going to need calculus. And that's because the shape of the walls and the shape of the roof, both of them, the shapes are constantly changing, and even what constitutes a wall versus a roof is not entirely clear in this building. The equations below represent an application of calculus called finite element modeling. Let's try something else. If I want to build a simple airplane, I can do it without calculus. I just want to make sure that the flight in a constant, steady state remains stable. That's fine. On the other hand, if I want to build a supersonic fighter jet and make sure that it can handle deadly spins and rolls, and I want to do all of that without ever actually building the jet, I'm going to need calculus. The equations below represent the so-called Navier-Stokes Equations, and they allow us to build conceptual models of airplanes inside a computer and test them. Test them for a variety of changes, change in airspeed, change in altitude, angle of attack, and even the shape of the wing. That needs calculus. Let's try one more. What we have here is the trajectory of a simple rock that someone throws up into the air. And you learned in Algebra 1 how to model that parabolic trajectory. You don't need calculus for that. On the other hand, if you want to throw that rock to the moon, or more properly a rocket ship to the moon, you're going to need calculus. The equations below represent the so-called three-body problem, which allows us to model the trajectory of three different bodies as their interaction, their gravitational interaction, is constantly changing the forces and the distances between them. So now let's come back to what the visual part of visual calculus is about. Visual calculus is simply this. We explore graphically, using simple geometries, all of the major topics of differential and integral calculus, including their relationship. Using a single extended example of traveling in a car, by the end of this mini-course, you'll have a framework for how all of calculus fits together. It's the best introduction I can think of for a traditional AP or college-level calculus course. And it all starts with a road trip. So fasten your seatbelts, because here we go. As I said, we're going on a road trip. Now, when I was growing up, the most exciting road trip we went on was from where we lived down to my grandmother's house. And as you can see from Google Maps, that took about 4 hours and it covered about 200 miles of distance. So let's make a graph. The distance from my home versus the time. And let's assume this is what the data looks like. It tells me how far we'd traveled after 1 mile. After 1 hour, we'd traveled 50 miles. After 2 hours, 100 miles, and so forth. And let's see what we can learn by analyzing this graph. Now, before we get started, I want to put a question in the back of your mind, and that is, hopefully you remember this very simple formula. Distance equals rate times time. And we've got a graph here that shows distance versus time. The question I'd like you to think about as I'm speaking is, what happened to the r? Where is the r hidden in this graph? I'm going to connect these dots. Now, what can you tell me about the steepness of this line that connects up the data points? Well, I hope you remember that the steepness of a line is something that we call slope. It's traditionally written as a fraction, which is the so-called rise divided by the run. And by rise, what we really mean is the change in y, or the vertical axis, divided by the change in x, or the horizontal axis. So what's the slope of this line? Well, this point here at the end would be 4, 200, 4 hours, 200 miles. The beginning is 0, 0. So how much does the y change? Well, it's 200 minus 0. How much does the x change? It's 4 minus 0. Gives me a change of 200 over 4, which simplifies down to 50. Now, what about the units? Well, they're the y units over the x units. In this case, miles divided by hours. Miles per hour. So what does the slope represent? Well, it represents how fast I'm going. And at this point, I hope you can see what the answer is to the question I posed. Namely, the r in the d equals rt formula is in fact the slope of a d versus t curve. I'm going to write that down because that's going to prove to be very important. Namely, in a d versus t graph, the slope is r. Now let's just do one other thing. I want to point out that we didn't just need to work with the endpoints in finding the slope. We could have worked with any pair of points along this straight line. For example, this point here is 3, 150, and this point here, after 2 hours, we'd gone 100 miles. So I could just as easily have found the slope by calculating the change in y over the change in x between these two points, namely 150 minus 100 over 3 minus 2. That would have also given me 50 over 1, and the units again would be miles per hour. One thing you notice if you think about the last graph that we drew is part of what makes it unrealistic is that people don't drive at the same rate for an entire long trip. So I've drawn a new graph here where, as you can tell, the slopes and therefore the rates of travel are different. Let's just take a look at this. I'm just going to label the different points. This is going to be 0, 0. This would be 1, 70, 2, 140, 3, 140, and 4, 200. Now, I'm not going to calculate the slopes for every segment, but I would invite you to do that, just to make sure that you're up to speed, on calculating slopes. I do want to focus on one particular segment, though, and that is the segment right here. What is going on here? What does this flat slope mean? Well, let's use the slope calculation. And we had that slope is the change in the y over the change in the x. So the y goes from 140 minus 140 all over 3 minus 2. That's going to be 0 over 1, or 0 miles per hour. Okay. So we're not going anywhere. What probably happened, again, if you go back and calculate these slopes, what I hope you came up with was that this is 70, this is 70, this is 60, and this is 0. What happened is you got off to a good start for a couple of hours and then you stopped. You stopped for lunch. So we could call this the Wendy's effect. And then when you restarted, maybe traffic was heavier, so you're only going 60 miles an hour instead of 70. Okay, but the key point I want to emphasize here is this stopped situation, and that is, let me just state it explicitly. In a D versus T graph, okay, a flat line implies a rate of 0. Now we're going to give that a special name, a special phrase to associate with that. We're going to call that being at rest. And I just emphasize that because this is going to come up in future problems. Remember, when you've got a flat line in a D versus T graph, you are at rest. Let's just do one final example before we wrap up, so I can illustrate one or two final points. So here we've got another D versus T travel graph. And one thing you might notice is that now the slope is changing on the half hour. And so, for example, if we were trying to find the slope from here to here, then the calculation would be what? Let's see, slope. That's going to be 200 minus 180 over 4 minus, in this case, 3.5. It's going to give us 20 over 0.5, or in other words, there at the end, this person's going 40 miles an hour. Okay? But the more interesting pair of points is here. Okay? Let's just take a minute to think about that. 2, 150. And the stop point is 2.5, 140. So when we do the slope calculation in this case, we're going to get 140 minus 150 over 2.5 minus 2. Negative 10 over 0.5. That makes our rate negative 20 miles per hour. So we can have negative slopes on these graphs, and they correspond to a negative rate. And because we can have negative as well as positive rates as well as 0 rates, we're going to use a special word with a specific meaning in this context to talk about rates. And that word is velocity. So let me just say this. In a D versus T graph, the slope is more precisely called the velocity. And in particular, we are not going to use the word speed. That's because we're going to reserve speed to mean things that can only be positive and do not indicate a direction, whereas velocity will be reserved for things that can be positive or negative and indicate a direction, forward or backward in this one-dimensional case, but more generally it could be a more detailed direction if we were working in 2 dimensions or 3 dimensions. So velocity, not speed, and let's note the fact that we can have negative miles per hour. It's our custom to have at the end of each video a short review of what we've covered. But because this introductory video has been a bit long already, and because the concepts are pretty straightforward, I would just invite you to spend some time walking down through these 6 points. Make sure that you are comfortable with what it is that you've learned.